name is Roberto Duarte Cuello. I'm a postdoc at the University of Edinburgh, working mainly in the lab of Professor Joanna Wardlaw. And my focus is on the quantification of enlarged perivascular spaces from brain MRI, and I will be talking about this. So first of all, I will explain what is perivascular spaces and why we care about them. Then I will explain what are the methods that we use and how we validate these methods, and then how you can share these developments to other people and improve the impact of your research. So first of all, perivascular spaces are fluid-filled spaces surrounding the walls of the blood vessels. These include a variety of pathways around arterioles, capillaries, and venues in the brain, along which a range of substances can move. It's related to the lymphatic system. That is a hot topic at the moment in brain MRI. So they are bright in T2 weighted images, and they are hypointense in T1 on FLAIR. And we have some more examples here. So you can see these small dots in T1 that are dark. They are bright in T2. They are also elongated. So it's more like tubular objects. And they look dark, but they are less visible in FLAIR. Okay, why are they important? So doctors have been associating these enlarged perivascular spaces with the degenerative, neurodegenerative disorders and diseases, and they are key component of the lymphatic system. It's a novel target for therapeutic strategies. That means that it could open a door to treat these diseases. Because they are early signs of dysfunction. And the evolution of these perivascular spaces may indicate progression or regression of a disease, telling you if a treatment is working. Why is so challenging? Well, first of all, we work mainly with already acquired data. This means that there is no homogeneity in the acquisition of the parameter, the resolutions, the sequence. These are small objects, so any imaging artifact like motion or noise can be distorting the information that we have in the scans. Also can be confused with other markers of brain dysfunction, like wide marker intensities, lacunae, and mineral depositions. How we measure them? So doctors have developed a scale that is a visual scale. So the way they do it is by counting how many PVS they see in a slice. But as you can see, they cannot go through the whole brain because it's a tedious work. It needs to be done by specialists, so they cannot analyze a lot of scans. The sensitivity is reduced because you're only looking at one slice. And then if you do it continuously, then you start missing counting, and there's a lot of human bias because if they see a lot of disease, even if they are not PVS, they start giving different ratings. So the inter-observer reliability can vary depending on how you do it or who does it. So we're trying to move to more computational methods. So in the group, Lucia Ballerini proposed to use a filter called Frangi filter that looks at tubular objects in 3D images. So what it actually tries to do is use the Hessian of the image, and using a combination of the features of the Hessian and different scales can tell you if a voxel is likely to be a PVS or not. And there's other type of methods, sorry about this, or other types of methods that look at the morphology using openings and, path opening to produce a path looking at tubular objects. So these are more reliable, well, at least in my experience. And we similarly take this output of the filters and threshold it to obtain a segmentation. So how can we validate these methods? So when I started working this project, the first thing we did is try to validate this. So I developed a model of a perivascular spaces looking at firstly a cylinder, and try to add it to a simulated scan. This allowed me to play with the dimension and see how is the limits of the filters we use. So in order to validate this, we also rely on a physical phantom that was developed at UNC Utrecht to compare. We saw a good agreement, and we use the in silico phantom now to try our filters, see the limits, see where they don't behave correctly, and analyze if we can measure PVS in a reliable way. Firstly, we compute the segmentation of the simulated phantom, and we compare it to the physical phantom. In the left, we have the results of Frangi. In the right, we have the results of Rorpo. So we see agreement. It's a better agreement for Rorpo. So that's why I'm saying I prefer Rorpo. We also can say what are the limits of the objects we can capture by producing a lot of small tubular objects and see where the filters start failing. So at a resolution of 1 millimeter, and using the model that we have with partial volume, we actually can go lower for Rorpo, and for Frangi, we can go around twice the voxel size. So that's a good thing. We actually can measure the diameter and length and see how aligned to the ground truth are they. So both follow the same pattern, so that's a good thing. But what we learn from the phantom is that we can evaluate the morphology of perivascular spaces. And because of the parameters we analyze of the filters, we saw that there's a big influence in the resolution and the contrast in order to select a threshold. So for automation, we know normalization will be a key. So for data sets with different contrasts, we will require different thresholds. For bezelness, parameters should be adapted according to the voxel size, different threshold. And for different resolution, the bezelness scales will be key because we care about perivascular spaces that are from 1 millimeter up to 3 millimeter of diameter. And that motion artifacts are more affecting of the PVS segmentation than the region noise. And maybe some post-processing will be needed to reduce false positives. So this whole computational pipeline has been developed in the group for a long time. It started with a systematic review in 2013. And we will be developing tools to make this process completely automatic. So we went from defining the region of interest, that would be the basal ganglia and the central semiovale and the midbrain, with automatic parcellations like free surfer, FSL, and SynSec. We validate this region of interest, the dimension of the PVS to be correct. We analyze this in cohorts that have disease, so we know where the methods fail, and we try to address them. And we continuously make QC of all the processing that we do. So all this work was encapsulated to increase robustness and reliability and to share with other groups. So how is the computational PVS pipeline? So it goes by taking the input image that could be T1 or T2, normalize the image. If we have flare, we normalize the flare image and combine it to the original image. This is to reduce the effect of the lesions. That would be white matter intensity. Then in both normal appearing white matter and white matter intensity, we will look at the PVS with the bezelness filter, either Frangi or Rorpo, select a threshold for each region of interest. And with that threshold, we will produce a segmentation that further will be post-processed evaluating for the size and morphology of the PVS, and also intensity based, because when we are doing the threshold here, we are losing some information in the intensity. And from there, we have our PVS segmentation mask. From there, we use our model to measure the diameter and the length. In some cases, we can even look at tortuosity and diameter to length ratio. So how we say that we're doing correctly? So as I mentioned before, we have visual scores that were done in different data sets that we have in the group. For example, the mild stroke study 3, the stratification cohort that looks at depression, that's called straddle, and IPA, that is an Alzheimer's disease cohort. So these were evaluated by doctors that look at the perivascular spaces and count them. And we can see that there is a straightforward correlation, linear correlation between basal ganglia visual score and the basal ganglia total volume obtained by the computational PVS pipeline. So this tells us a lot that we are actually going in the right direction, because doctors already evaluate this looking at disease, and the association are already established. So having this correlation tells us that we're going in the right direction. But then we only tested in our internal data sets. So how can we ensure reproducibility and share to other researchers? So we decided to encapsulate this pipeline in a Docker container, also export through Singularity, because some universities have some privacy concerns about Docker. And we actually added the parallel implementation so we can process multiple scans at the same time. And we started a collaboration with different groups in the world that are interested in segmenting perivascular spaces. Mostly there are groups looking at diseases such as Alzheimer's disease, multiple sclerosis, small vessel disease, mostly brain neurodegenerative diseases. This was really organic because people know that it's a challenging task to segment perivascular spaces. So there was the lack of tools. So we started this collaboration, and we are refining this pipeline constantly. And thanks to sharing these tools, I can tell you that it's a great thing to progress science. So we'll be able to perform a new systematic review on perivascular space methods. We've been able to compare them to small subcortical infarcts, see the role in Alzheimer's disease with retinal phenotypes in sleep apnea, ALS, produce some comparison with different PVS segmentation methods such as Roberto, German filter, Frangi filter, a topological relationship between the PVS and Y intensity. We are able to develop deep learning PVS methods. We actually analyze PVS in relation with post-COVID syndrome, and another evaluating the treatment of sleep apnea, such as CPAP treatment. So this is thanks to sharing the code and be able to reproduce the results that we're having. We actually proposed a challenge for perivascular spaces in 2024. We just submitted another challenge for MICAI 2026, so hopefully we'll get approved, where we provide a different data set, a subsample of a lot of data sets, the different acquisition, different scanners, to test all the new methods in deep learning and see how they perform. Unfortunately, there's a lot of room to improve. We're still on DICE 0.44. That's really low for the best method. We're trying to be open about this and try to promote the groups to share their code. And I would like to end this presentation with some future work because this is a hot topic at the moment, and everybody's interested because we will be able to, if this works, to catch disease at early stage. So it's a quite focus now at the neurodegeneration research. So we're combining different sequences to be able to look at PBS that are inside of the lesions. So by having this kind of images, we can look at the disease and look at the progression of the lesions. So this is quite interesting. Also, we are trying to improve our pipeline to be able to fit curves and analyze tortuosity, as I mentioned before. But this needs to improve robustness because it works when you tune one by one the images, but you cannot give that to other researchers because then there is a problem of reproducibility. And yeah, I think that's all I want to say. Thank you for listening.